questions at all? Let's see the number. Yes.
I was wondering about number 12.
That's a good question because that is vector addition and we're going to be talking about that today. Number 12 and subsequently number 13. Oops. 12 and 13 are both a little tricky in that they factor in a minus sign. So we'll talk briefly about what that means. Let's see. For 12, you've got 6 miles and 120 degrees. So that would look something like this. Subtract 4 miles and 30 degrees. If you're subtracting, then it should work against all of these directions here. So, okay. If we were drawing them tip to tail, normally 4 miles and 30 degrees would look like this. So, well, we will be talking about this in further detail today, so this is not the only time you're going to see it. We'll look at these questions more closely in a minute. But when adding vectors graphically, you should draw them tip to tail, and if one of them is negative, take what it would be when drawn tip to tail and invert it. So that would instead make it, instead of being 30 degrees counterclockwise from positive at x, it would be 30 degrees counterclockwise from negative x.
Okay.
Yes.
Do these start like the angles start at like 0,
Yes,
like on the X?
correct. Every angle on this particular assignment would start from whatever point you're starting at, as if beginning from counterclockwise from x, unless otherwise indicated by a minus sign up until over 13. Briefly, so 12 would look something like this. 13. I'll do better drawings in a second. I'm going to pull up the graph on the board and look at things one at a time. 13, because we're multiplying, that would be 8 miles and 30 degrees. Followed by 3 times 6 is 18 miles in this direction, but because we're turning it would actually be in this direction. Again, we will examine these more closely. I promise you that. Does this at least help with the original question?
Yes.
Okay. Yes, today and next Wednesday as well, we will be looking specifically at vector addition, how to do it, what it means, how to do it graphically and mathematically, and all possible related things. That is the item of the day. Any questions? Any other questions before we get started on vector addition today? Okay. So, I don't know why my straight edge from before vanished. have described vectors as a quantity possessing a magnitude and a direction. So, pressure, vector, magnitude, plus direction. Sometimes that direction will be a cardinal direction, north, south, east, west, x, y, z. Occasionally, though, that direction can be a two-dimensional vector. It could point in more than one axis at once. We're going to see a lot of different types of problems, and we're going to work several examples together. So single vectors could point in about any direction that you could imagine. And when describing a vector, you need to write both the number, magnitude just means the number itself, and you need to specify what direction it's in. Typically, not always, but typically, those directions are described as an angle counterclockwise from the x-axis. You can describe them other ways as long as you are specific in your answer. For example, let's say that we were looking at this type of a vector, which is listed as being 60 degrees from the positive x-axis. You can write your answer as 10 meters at 60 degrees, and if nothing else is further specified, the assumption is that that 60 degrees is from the positive x-axis. But alternatively, if it's 60 degrees from the positive x-axis, it could also be 30 degrees from the positive y-axis. And you could describe it as such as long as you were very specific in your answer. So these two answers mean the same thing. Yes.
So when we graph these on our paper, do they need to be like, you're able to take a protractor and measure an angle, or are we just doing it like closest to what it is and then writing the angle in there?
For the ones that ask you to solve graphically, it's a small box, and I don't expect everyone to have a protractor on them at all times. So if it asks you to solve it graphically, I would ask for as close a picture approximation as you could create. You don't necessarily need to perfectly, I am not asking you to perfectly, with a ruler and protractor, measure it out, and then find the answer using the ruler on what you drew.
I've never seen these and I don't even know how to get them.
That's why we're here today. But graphically speaking, if we were adding these two vectors together, the answer would be this purple arrow. The goal is to figure out if someone walked this long in this direction and then turned and walked this far in this direction, the goal is how far and in what direction are they from start to finish. So the answer to the graphical side of 12 is this, and the graph is largely to assist in the math because we're going to break these vectors down into triangles. For 13, the graphical answer would look like that. And I will show how to turn these into trigonometric triangles and find the numerical answer. You don't have to do that protractor style. With that said, so let's go ahead and start talking about how to do that so we can get through it today. So I put up here a quick sample question where we are going to add vectors together. So, sample question says, what is the vector displacement from start to finish after someone walks 5 miles north? So starting from origin, we're going to go 1, 2, 3, 4, 5 miles north. Call that range 1. Then 3 miles east, 1, 2, 3, range 2. 8 miles south, 1, 2, 3, 4, 5, 6, 7, 8, range 3. 10 miles west, 3, 4, 5, 6, 7, 8, 9, 10, and another 5 miles north again. This is a very winding way of getting where you're going, and there's two ways that you could look at this question. If you were asked, how far did this person walk? There's two ways you could answer the question. Because you could talk about it either as a scalar distance walked or a vector displacement start to finish. If this particular person had an odometer attached or like a step counter attached to them, what would the answer be for, like, what number would the odometer display for total distance walked?
So instead of going from the start to finish, you're like basically counting everything.
Yes, if we were looking at, for example, scalar distance walked, this would be like what your car's odometer tells you or your step counter tells you. This doesn't care about direction. It just cares how many times did the tire spin, how many feet elapsed did this person walk. I'm actually going to relabel these and apologize. This is 5 miles, that's 3 miles, that's 8 miles, that's 10 miles, and that's 5 miles. If we were looking at just this person's or this car's odometer, they traveled 5 plus 3 plus 8 plus 10 plus 15, that would be 41, sorry. 10, 20, oh, 31. Is that right?
Okay, yeah.
Okay, I didn't hear what you said, I'm
No,
sorry.
you're good. I just heard the 40s, and I was just like, wait, let me bring from.
Oh, I make mistakes, I am human. So scalar distance walked, I was about to write the 4 again, 31. But scalar isn't a vector, sorry. Distance is not a vector. Your car's odometer doesn't care about direction. You could drive around in a circle, like, okay, better example actually. When you get in your car and you drive anywhere, and you eventually drive back to where you started, your odometer will show miles driven, even though your displacement from start to finish will be what? 0. Because displacement cares about direction from start to finish. Scalar distance does not. So to find the displacement from start to finish, we care specifically about the straight line from here to here. We want to know how far apart those 2 points are, the actual net gain after this whole process. Will this be as simple as just adding the numbers together? Probably not. That's because when looking at vectors, you can only add numbers in the same axis. Hypothetical question. I am going to walk along the classroom. I'm currently about 1 or 2 feet away from the board. So let's consider this the x-axis and this the y-axis. I'm now going to walk parallel to the board along the x-axis. Am I any closer to the board? No. My displacement was entirely in the x-axis. That had no effect on my y displacement at all. So you can only add together things that are in the same axis. So let's say I just walked 10 feet in the X, and now I walk 5 feet in the opposite direction. I'm still no closer to the board, but that 10 and that 5 do work against each other, and now I'm only 5 feet away from where I started. These units are not to scale. So, you can only add numbers in the same axis. That means we need to look at the X displacement separately from the Y displacement. So, what are all of our X vectors for our travel? 3 and 10, very good. So, should we add 3 and 10 together?
No.
Almost.
Oh, no.
They are in the same axis, but technically in the opposite direction. So, vectors care not only about axis, but also direction within that axis. So,
7.
very good. I'm going to get just a tiny bit more specific. Is everyone okay with using Greek letter delta to mean change in? So delta x, we moved 3 feet in the positive x direction. We then moved 10 feet in the negative x direction. So we have, when doing questions like this, you do need to decide what direction is plus, what direction is minus. Typically, that's going to be right is plus, left is minus. You could switch that. If you do switch it, you need to be consistent for the entire duration of the question. Yes?
Wait, so don't use like east and west?
You could use east and west. So when I write, okay, in a second I'm going to write -7 in the x-axis. That is one way of describing the answer. The negative tells us, the x-axis tells us the axis, negative tells us which of the two directions in that axis. We could write this as a completely acceptable answer, ditch the negative and just call that 7 west. Because west says not only axis, but direction within that axis. So, how you write your answer becomes important. Either of these are acceptable to describe the x displacement in this particular question. The y displacement, we walked 5 meters north, 8 meters south, 5 meters north again, which gives us a grand total of 2 meters in the positive y-axis. You could write this as 2 meters north. Either way, it's in the positive direction. We are northward, we are positive y away from where we started in the y-axis. And these two components together, -7x and the 2y, give us the graphing coordinates for where we end up. 1, 2, 3, 4, 5, 6, 7 in the negative x direction, and then 2 upwards in the y direction. So doing this told us the coordinates of where we wound up. That is, that tells us where we are. Any questions so far? Okay. So the graph is to help reinforce that this is what we have found. The graph can also help with taking these coordinates and figuring out the actual displacement along that hypotenuse. Because what we've effectively created here is a triangle where the x leg is -7 and the y leg is +2. So if we wanted to know, if we took a tape measure straight from this part of the pathway to this part of the pathway, how would we get that number, that length? Diagram theorem. Not a trick question, I promise. So, -7 squared, the negative is going to get squared away, so it being there is fine. Plus 2 squared equals c squared. We'll get a number for c. There goes my calculator. So that is the distance in a straight line from where we started to where we ended up. It's just the net displacement between those 2 points. So that tells us the magnitude of our displacement. However, we have been asked for the vector displacement. Vectors have magnitude and direction. So to have a complete vector answer, we need to determine the direction that this distance is pointing in. But what we've created is a triangle, a right triangle, and we know all 3 sides. And we know which angle is the right angle. So, what we need to do is employ just a tiny bit of trig, and we can figure out what direction our new vector is pointing in. I would recommend tangent of theta equals 2/7. So theta will equal inverse tangent of 2/7. That's going to be 15.94 degrees. And that not only tells us how far we went, but in what direction. So that is now a vector answer. There's one teeny tiny hiccup, and this is not a tremendous deal, but this number is not in terms of the positive x-axis. So writing this number is fine. If I was giving this as a test answer, I would modify this slightly by saying at 15.94 degrees clockwise from the negative x-axis. That describes which direction, and then further from that, either counterclockwise or clockwise from that starting axis. You could also describe this as clockwise from west, if you wanted to. That's a lot of information so far. How do you guys feel? At least a little bit on it. Yes.
So you said clockwise from west, which is kind of like the same, like you just keep saying like south from west. I don't know, is that like, I don't know how to look in terms of that, like not being dumb, like is that south, or is that like making
South.
a new direction?
Okay.
I don't know how to tell like which way that would be.
You're right. There's a lot of different ways to describe the angle and then what the angle is from. We could describe this as clockwise from negative x. We could describe this as clockwise from west. We could further describe this as 15.94 degrees north from west. because you start west and then you tilt this far north.
So would that just be like northwest?
If you were reading a map, you could just say northwest.
Okay, I just couldn't.
This
figure
would
out
be
if I
closer
could
to
do that.
west-northwest, because some maps divide it up into like northwest, and then at the 30-degree mark, north-northwest, and then at the 60-degree mark, west-northwest. You could definitely describe this as northwest. It's just that doesn't necessarily tell you if this is from, like,
Closer
tipping
to
up from
whichever-
west or away from north. So this is the better, more mathematically accurate way of writing it. And I'm just trying to help future-proof all of your answers to err on the side of specificity. This could be written as north from west. If you were looking at numbers 14 and 15 on the homework, that describes something south of west, which would be starting at the west axis and then measuring an angle towards the south from there. I will fully admit, the directions might be the trickiest part. It is okay if it takes you a second to stare at them. It is okay if you need to ask me for elaboration. I don't mind showing you sketches to help establish what everything's pointing towards. This is a very visual assignment. And if you are worried about drawing if you're worried about this is my picture, did I do it right before working forwards, please show me your sketches. I will give you the thumbs up or tell you what needs revision. I will even tell you, if you find your answer, I will help you figure out, what it's 30 degrees from, how to write your answer. Please communicate with me. I want to help you. I want to help you understand this, because that's the entire purpose of this class. If it comes down to it, it'll even delay the homework if we need to spend next Wednesday just going through how to write all of the answers. How do you guys feel about this kind of question? Okay. I had a different sample prep, but I'm actually going to switch gears slightly, and let's actually look at one of the homework problems instead, so that you actually get an answer instead of just a sample question. I like starting with something like this to show how just walking along the proper axes, it still leads to this type of an answer. But now I want us to actually add two two non-cardinal vectors together to show slight differences in the process. So let's look at homework question. It's labeled as number 11, so I'm going to call it number 11, even though the assignment skipped from 6 to 11. Point is, I don't know why I'm hung up on that. We're looking at number 11 together, and we're adding two vectors together. When adding two vectors, my recommendation is draw them tip to tail in the order that they are listed. So from start to finish, we are told for number 11, we are starting with vector A and then adding vector B to it. Two vectors are given above. Vector A is 4 miles at 30 degrees. Vector B is 6 miles at 124 degrees. So when looking at these, start with the first one listed and draw it from the origin first. So for number 11, we're looking at vector A first. That's the 4 miles at 30 degrees, 5 degrees, 30 degrees. Why am I humming on this? Just go for it. So this is vector A. and the actual line of this triangle is 4 miles. That is the length of the triangle we have drawn, yes.
With the number, so whatever number that is, it's just, so we'll just write that number like right there on the side, like for help, or I didn't, before I couldn't tell, like, does the 4 go through like an x-axis or a y-axis, do I need to exactly count 4 squares?
For these questions, you don't have to worry about the numbers matching the grid. Don't stress about that. I can't freehand it. I got hung up on it a second there before I realized I just couldn't afford to worry about it, or I drive myself insane. So, official mandate for drawing pictures 11 onwards. They don't need to perfectly match up with the grid. The numbers are mostly there for the first page of graphic questions. But we have drawn vector A 4 miles along this hypotenuse. This is the hypotenuse of a triangle. This angle would be 30 degrees, as we drew it from the x-axis. And then, when I say that we should add these vectors tip to tail, I'm referring to the way that I draw the vectors when adding them together. So I'm going to do I'm going to do B in blue. From the tip of the vector we just finished, we now put the tail of the second vector. I'm going to put in a little mini coordinate system here just to help me with the sketch. So from that spot, vector B will now be formed, and that is 6 miles at 124 degrees from X, so 90. It would look something like that. Now I see why someone might have thrown the string out of the way, but I'd like it to remain within reach. So that thus far is drawing our 2 vectors. If someone was walking this path, start here, walk 4 miles in this direction, and then 6 miles in this direction, they would end up here. So graphically speaking, the final answer would look like this in purple. So that's the line that we're looking for. We want to know the magnitude and direction of that purple line. Now to actually find that, we're going to need to do some trig. Because we cannot add 4 to 6 and call it a day, because these vectors don't point in the same direction. They each of these vectors move in both the x and the y-axis at the same time. Both of them have x and y components. So we need to divide each one up into its components using trig. Then we can add the x's with the x's and the y's with the y's. My computer just died without telling me. Thanks, Bill Gates. It's okay. We've got the arrows up there at least. Either work or don't. The inconsistency is driving me crazy. Stay. Good dog. we need to break these vectors up into their x and y components, because we can only add x direction, and y direction to y direction. So each of these two-dimensional vectors can be represented as a triangle. Once in the entire time I've worked here, has that worked? So I'm going to call this line the x component of vector A, ax, and the y component of vector A, ay. For this particular triangle that we built, it is a right triangle, x and y are always 90 degrees from each other. We know the hypotenuse of this triangle we've drawn and one of the angles, so we can pretty quickly trig our way to getting ax and ay. Sine of 30 degrees should be a y over 4, and cosine of 30 degrees is a x over 4. And those will tell us the x and y components of this triangle. I have ay is equal to 2, and x is equal to 3.46. And I will draw those up on the screen as well. So we've divided up the first vector. We now need to do the same with the second vector. And there's a dozen different, I was just using this. Nope. Okay. Vector B is green now. So we have Bx and By.
Why are we making more triangles? Well, it's crooked.
Yes, these vectors, the two vectors we're adding are crooked. Neither of them is entirely in the x and neither is entirely in the y. Some of this one is in the x, some of it is in the y, and same for the second one. So if we wanted to know the distance from start to finish, we're going to need to know how far in the x each one points and how far in the y each one points. So eventually, this y component plus this y component will be the same as the y component that represents our final answer. We call that cy and cx. Every single one of these vectors is a triangle. It's either a triangle or it's a line in a cardinal direction. Yes?
So, I guess just looking at it, I thought we were doing like the A and the B, like those were sides, and then we would just solve using the Pythagorean theorem. But why can't we do that?
We can't necessarily do that because this is not a right angle. A, B, and C in this case don't form a right triangle, or at least they won't always. So by and large, dividing each of the vectors we're adding together up into their xy components, adding those components together is the surefire way to be able to do this for any question. This will help you. This is the surefire way to add any two vectors together. So for vector B, oops, I'd like to get to an answer quickly for you guys. The way that I've drawn vector B, you don't necessarily have to do it exactly the same way, but the way that I've drawn it, the 124 is not actually inside of the triangle that I drew. So I've found the complementary angle to 124, which is 56, and that's the actual piece that's inside of the triangle. You don't necessarily have to do it the same way. I could see a student absolutely putting by here and bx up here, and that would give you a slightly different angle in there. That's completely fine. This is just the way that I've got it drawn. But if this is the interior angle that we know, moving forward from there, we could do sine of 56 equals by over b's total length, which is 6. Cosine of 56 is x over 6. So, to quickly get you to an answer. Got by is 4.97. X as 3.36. So, to solve for vector C, to solve for their added form together, what one must now do is we can take the xy components and now begin adding them together. So let's look at the x's. Cx, the x component of C, is going to be the sum of the x's of the other two vectors involved. Ax was given as 3.46, and we're going to add that to bx, which was 4.97. Is this good to go with no problems?
When you draw the triangle, like see how AX is going to the right, how do you know if it, how do you know it goes to the right? Or does it not matter anymore? I don't know. Like,
How do I know that AX doesn't point that way?
yeah. And same thing for the other triangle. Like, how do we know which way? Because that'll change our answer, right?
It would, you're right. And I also wrote down the incorrect BX. BX is 3.36. That's unrelated, but I'm fixing it now. So, when we were first drawing these, vector A was described as 4 miles at 30 degrees. In order for A to be pointing that way, northeast essentially, we would have to be going east and north. Meanwhile, with vector B, since that one's heading northwest, the two components would have to point north and west.
So that 3.36 is be negative?
It does, in fact, because the two x components of these two vectors are working against one another. If someone was walking along this trail, it's strictly in terms of the x-axis, they turn around for leg B. So that makes the final x component of vector C 0.10. Go ahead and write that as in the x-axis. And we'll do the same thing with y. It's a little simpler for y because both vectors point north. So both of these y components are positive and they will add together normally. This person was consistently walking north the entire time. So CY is given as 2 plus 4.97, so that should give us a total of 6.97 in the y-axis. And so, for our final answer, vector C can be successfully written as, open parentheses, points 10, comma, 6.97, close parentheses, miles. And that is ultimately the displacement in both axes for this entire walk in the park.
Do we have to put vector, I don't know.
For now, I'm going to say we can leave the answer like this. This is technically a vector answer because we've specified magnitude and direction in 2 axes.
Do we also like, when they have values? Like we did the last question?
Yes, I'm going, I want to try to simplify this a little bit for you guys while you're working, but before we meet back up again, to help simplify this just a little bit. Writing the answer like this is a vector answer because you've specified distance and direction for 2 separate axes. Writing it coordinate style is a legitimate vector answer. And all that is technically asked of you is the vector displacement, not the distance, not the number, just the vector displacement. So for right now, that answer satisfies. So for the time being, we will go further into detail and work more of them together when we meet back up. But for right now, that is an acceptable answer.
So by doing this, we've solved it mathematically and graphically?
Correct.
Okay, is graphically just like writing it on the graph, basically?
Yes. This picture suffices for graphically, this number suffices for mathematically.
And this is not do next Wednesday, I want to say, or is? Was it supposed to be due next Wednesday?
Yeah, I read one.
Yeah, I think my original intention was next Wednesday.
I can't remember,
but-
all these like extra days or
No, I'm going to make it next Friday because there's a couple questions on here that aren't strictly what we just did that I'd like to talk about. So, official disclaimer, this assignment is due next Friday. Next Friday. You don't have class this Friday. It'll be due next Friday, calendar day, April 9th. Because this Friday is April 2nd. Yes, next Friday is April 9th. Homework is due on April 9th, next Friday. Have a wonderful day. Please send me any questions you have while working this. Ask me if your pictures are okay. Please do it. Please email me. I'm begging you. That said, please also enjoy a nice long weekend. We all need it. Please sleep. I'm begging you to be that good.